Y26 quantum mechanics. According to relativity and the series of experiments, including photoelectric effect and the Compton's scattering, de Broglie introduced the idea the wavelength of a matter wave, such as elementary particles, such as electrons, if it carries the momentum, the wavelength is inversely proportional to the momentum, and the Planck constant that we already measured from the photoelectric effect contribute to the determination of the effective wavelength. And this wavelength can be measured according to the fringe, the diffractive fringe coming from the scattering against a fixed target experiment, something like that. So this de Broglie's wavelength, lambda, is not restricted to the non-relativistic case MV. Usual high school textbook, it's wrong because they assume students are not familiar with the relativity. They use the lambda equal h over mv. It is completely wrong. The basic idea of this kind of quantum mechanical treatment of a matter wave is purely relativistic, except for the photoelectric effect. The Compton effect is the decisive experiment to show the relativistic behavior, and from that on, we began with the idea of a quantum mechanical treatment. So the momentum is actually relativistic. It is not extended, it has not been extended from the non-relativistic theory. From the beginning, the theory was relativistic. In addition, photon's energy formula began with the relativistic formula for the unshell condition. By substituting rest mass equals to 0. So we cannot treat photon with non-relativistic theory. It is a completely relativistic theory. That's the beginning of quantum mechanics. So if we want to deal with the wave mechanics, wave nature of a particle, then we need a wave function. A function that has an argument x minus vt, or if you prefer a sinusoidal wave, that is the simplest expression, then we have to use the argument to kx minus omega t. And if it travels in 3 dimensions, we modify this one as a k vector dot x vector minus omega t, something like that. However, we will find a very interesting idea. Lambda h over p, okay, p equals h over lambda, and p equals h over 2 pi, and 2 pi over lambda. That is h bar k. Momentum and wave number are related. They are proportional, and proportional constant is h bar. We have energy of a photon, h nu, and h over 2 pi and 2 pi nu. And what is that? Omega, h bar omega. Aha. Energy is related to angular frequency. Momentum is related to wave number. There is a common factor h bar. Why don't we express any kind of wave? Any sinusoidal wave is expressed like that. And we divide it by h bar and multiply it by h bar. What's that? I over h bar px minus et. Oh, and why don't we replace this one? E over c and ct. Oh, it is very familiar to us. What's that? Minus, we pull out minus E over c ct minus p dot x. It is a scalar product, relativistic 4 vector. Why? E over c comma p, scalar product with the ctx. Haha, it's a p mu x mu, scalar product of 4 vectors. Actually, what we learned for the wave from the non-relativistic theory was completely invariant quantity, Lorentz invariant quantity in relativity. So this is a relativistic notation for momentum is used to construct de Broglie wavelength. And just before, Compton scattering confirmed the expression for the relativistic expression for momentum for both photon and electron. And at the same time, Davison and Germer carried out the experiment to show the fringe pattern of electron scattering. So this is another experimental evidence of matter wave. Finally, Max Born, we use quantum theory with the wave function, and the Bohr's basic idea of electrons orbit was completely wrong, and we now understand the electron's position by computing the wave function square integrated over space as a probabilistic treatment that was for the first time introduced by Max Born. So any textbook, current quantum mechanics textbook respects Max Born's achievements. Okay, so this is a very interesting historical stories. Please refer to this. We will learn a little bit about the Schrodinger equation, that is the wave equation for matter wave. However, it is a relativistic version of the wave equation was developed at the same time. And both of them received the Nobel Prize at the same time. Okay, let us go back to the Maxwell's equations. We had these four Maxwell's equations, and I do not want to do this calculation in this class. However, now Lorentz transformation is proved to be a correct transformation rule for space-time coordinate rather than Galilean transformation. And under Lorentz transformation, these four Maxwell's equation becomes completely covariant, systematic. So everybody is happy now. Now let us focus on Max Born's idea of treatment of wave function that is a solution for the Schrodinger equation, that is the wave equation for non-relativistic particle. It is consistent with the electric field square. When I taught you about the diffraction pattern, I computed the electric field coming out measured at a field point P on the screen by integrating all of the partial contribution passing through a finite width aperture. After evaluating the electric field, I squared it to find the interference pattern. It is basically the same idea. Just like what we did for the electric field, Max Born introduced the idea that the solution for this wave equation called the Schrodinger equation behaves like the electric field, and it's a complex number, complex wave function. So its absolute value squared is the probability. Actually, in here, probability of finding a quantum mechanical particle satisfying wave nature is something like the intensity of light carried by the electric field. And when we compute the electric field due to the many sources, partial contributions, we make an algebraic sum. And if we have many contributions, then we replace this summation as an integral over space, something like that. Just like that, any partial waves of a wave function can be added algebraically that respect the superposition principle of the electric field. So wave function can be added. And then the Broglie wavelength is used to interpret the energy and momentum. And just like what we have done already for the analysis of a plane wave solution expressed in terms of full momentum of a massive particle and the space-time coordinate called the forward displacement. Using that way, we can consider simplest wave that does not carry any spin or structure. That is a scalar wave that is because it is a function of sinusoidal function whose argument is nothing but the scalar product in 4 dimensions. And this is nothing but 1 over h bar p dot x. I already showed you. So this is 3 vector and this, and actually this h bar over I p mu x mu. Okay. So applying that idea, we were able to find that the wave function is intrinsically completely relativistic expression. Okay, so there is a sign mistake. There should be negative sign on both terms. Okay. This is a wave function. And now, when we consider wave in comparison with the particle consideration that we are familiar with for non-relativistic theory, in wave mechanics, one cannot measure the momentum and position simultaneously. The reason is that momentum is h bar k, and that is completely determined by the wavelength. Wavelength means is a sinusoidal wave with a spatial period that is a wavelength. When you consider the probability of finding a particle represented by this wave, e to the I kx minus omega t, its absolute value is 1 everywhere. So even though you are able to find the momentum, this monochromatic wave determines the momentum exactly. However, the probability density over the space is unity for all over the space. Determination of exact P gives you no information about the position of particle. This is called the uncertainty principle of Heisenberg. Okay, so it is if you treat the particles in terms of wave, this is fact. You cannot determine the position and momentum simultaneously. Okay, so if you want to find out the momentum from the exponential function, that is the simplest way, momentum is h bar k. So how can I find momentum, this wave vector k? We learned when we studied Maxwell's equation, what we have done is taking the derivative with respect to space. So that is a gradient. Gradient operator is applied, then you have wave vector. You don't like this imaginary factor, so we divide this I, and multiply h bar to achieve this, then it is a momentum. To read the momentum of a monochromatic wave, what you do is h bar divided by I, then gradient. If you want to read the frequency, what you need to do is to take the time derivative. But I need h bar omega to obtain the energy of the particle. Therefore, I need to multiply I h bar and time derivative to this plane wave solution. Momentum, this kinetic energy and potential energy can be computed from the wave function. How can I do that? Because momentum is h bar over I gradient. P squared is nothing but the Laplacian minus h bar squared, something like that. So substitution of this operator gives this one as a Hamiltonian. Hamiltonian is nothing but the total mechanical energy. The energy conservation, H, total mechanical energy, is kinetic energy plus potential energy. This basic idea was employed for Schrodinger to construct this wave equation called Schrodinger equation. Okay, this is called time dependent. We have time derivative, time dependent Schrodinger equation. He constructed this Schrodinger equation and studied various problems. And furthermore, we can also introduce a completely relativistic equation. This is energy over C is a square root of mc squared plus p squared. We just square this equation to find out this. And similar method can be applied to find the corresponding equation. This is very similar to the usual wave equation for light. And this is called Klein-Gordon equation. So if particle shows wave nature, such like diffraction or interference, we have no choice but to construct a wave equation that is satisfied that particle. This is a particle nature duality. And once you obtain this time-dependent equation, you can always, because the operators are added in linear combination, we can always apply this mathematical trick called the separation of variable. This separation of variable is not allowed if an operator has a mixed term such as first order time derivative with the gradient. This kind of operator does not appear in this physical problem. Therefore, fortunately, we can introduce a trial solution that is completely factorized. In that case, you will learn when you study differential equation, this kind of trick is always used. It's developed by mostly in physics problem. And substituting this one and divide by into the Schrodinger equation in here and divided by this the solution, then you will find the left-hand side is purely depending on time and right-hand side is purely dependent on x, and actually that has a certain value that is independent of both the time and space. This we call an eigenvalue. Eigenvalue is the characteristic value such as the characteristic frequency of the equation of motion for damped harmonic oscillator that we learned. Now that is identified to be the total mechanical energy of the system, and the solution is now finally expressed in terms of this. Because the time part is a trivial first order equation that whose solution is this. And full time and spatial dependence of the wave function can be expressed as a linear combination of partial waves, and this x-dependent term satisfies this time-independent Schrodinger equation. And actually, when we learn the vibration of a string, it has various normal modes. If there are n oscillators, we had n normal frequencies. A field of lowest frequency was identified to be the same as Pythagoras expected, and the higher frequency, you can see the Pythagoras theory is completely broken down. Just like that, all of the normal frequency contribute to this equation, and we have many solutions, and these are actually the basis, just like the basis of the Cartesian coordinates. These are the Cartesian coordinates, and actually these phi n's are basis of Hilbert space. Hilbert space is the space of wave function. We learned a lot. We learned Euclidean space and basis introduced by Descartes. We learned Minkowski space, that is the basis for the four-dimensional space that is satisfied by the relativity. And then when we study the wave mechanics, we learn that there are fundamental harmonics, and there are various frequencies that exactly the same thing happens in quantum mechanics because it is a wave analysis. So let me summarize. This is called the uncertainty principle of Heisenberg, that is due to the fact that if I bring in the monochromatic wave, delta p, error of determining momentum approaches zero. But because of this, if we decrease the uncertainty of momentum arbitrarily small, then the uncertainty of position becomes arbitrarily large to make the product of finite value. That is the nature. Mathematics never tell you. They could not tell you because their theory is human theory. That is exact, but that does not exist at all. Physics is treating the problem that exists in nature. That is the difference between many cases. You will find it looks like mathematics. However, it is absolutely different. Physics and mathematics is absolutely different.